connection between these objects and polynomials. So, Kuikui is going to give the next talk.
Okay. All right. Hi, everyone. Good morning, and thank you all for coming, and thank you to the organizers for inviting me to speak. So today I'll be talking about, as Cheyenne said, sort of connections between polynomials, high-dimensional expanders, and sort of some of their algorithmic applications, in particular to approximate counting problems. Okay, and this is based on joint work with Cheyenne, Nima Nari, and then Cynthia Vinzan. Right, so what are the objects that we're going to study? We're going to study matroids, which we've seen throughout the week. I think Professor Ardila yesterday even gave, like, I think 5 or 10 different definitions of matroids, all with like sort of their own usefulness and geometric beauty. But today we'll sort of focus on like one specific definition, which is sort of like the simplicial complex definition. So what is a matroid? You're given a ground set. You're given a collection of subsets of this ground set. And this collection, the elements of this collection are called the independent sets, and they satisfy 2 axioms, namely that any subset of an independent set is independent, and that they also satisfy an exchange axiom, namely that if you have 2 independent sets, one is larger than the other, you can take an element from the larger one and add and sort of augment the smaller one and preserve independence. Okay? And sort of, and we'll call the maximal independent sets the bases, and by the exchange property, the bases all have the same size, which we call the rank, and I'll use R to denote the rank. Okay? And sort of 2 sort of, I guess, classic examples that maybe you can keep in mind is sort of the graphic matroid, which is where your ground set are all edges of some graph, and then you have a collection of edges is independent if and only if it does not contain a cycle. And then another example, which is sort of, another example would be, say, the linear matroids, where your ground set are a bunch of vectors, and then subsets are independent if and only if they're linearly independent. Okay, so here in the graphic case, the bases are the spanning trees of your graph, and then in the linear case, the bases are, I guess, your linear bases. Okay. So what is the problem that we're going to study? We're going to study, you're given a matroid, and you want to estimate the number of bases of your matroid. And how is the matroid given to you? Basically, you're given, say, some function that says, you can ask this function whether or not, say, a given subset is independent. That's how you're given this matroid. It's sort of like an implicit and compact representation. So it's known as sharply hard to do exactly, and it's even known that, to use efficient deterministic algorithms, you cannot obtain some exponential approximation factor. So the question we're resolving is, can you get, say, 1 plus epsilon efficiently using randomized algorithms? Okay. So why should you care about this problem? So I guess one example comes from coding theory. So here, the setting is you have, say, a parity check matrix, and the kernel of this matrix gives all the code words in your code. And let's say you send these code words through some channel, some noisy channel, in which, say, some bits might become corrupted and they get erased. And you want to, and your goal is to, say, be able to recover from these errors. So you can exactly recover from these errors if and only if you, when you send your code word through the channel, the bits that get erased, the corresponding columns in your parity check matrix are linearly independent, right? Because then you can just solve a linear system to recover the bits. So in particular, for example, in this case, if you can count, say, the basis of a matroid, so in this case, the matroid would be the linear matroid given by the columns of your parity check matrix. If you can count the basis of this matroid, then you can, say, for example, estimate the probability that you'll be able to recover from such an error. Okay, so this sort of gives you a way to evaluate, like, how useful, in some sense, your code is. Okay. Another example is from, say, network reliability. Here, the setting is that, say, you have some network, some communication network, represented as a graph. The links, I guess, the edges correspond to links between, say, servers in your network. And, say, each link fails independently with some probability p. Okay. And what you want to do is, say, estimate the probability that your graph becomes disconnected. Okay. And it turns out that to estimate its probability, you can do this exactly by counting the basis of some matroid. Okay. And sort of, I guess, a third application that maybe probabilists care about is sort of the say, uniform distribution over the set of random spanning forests of a graph, okay, not just spanning trees. Okay. So there's been many previous works. So already even just in the graphic case for sampling random spanning trees or counting spanning trees. There are also many works that sort of extend the graphic case to other classes of matroids. And there are some other problems, say in the determinantal point process literature, where you can also cast this as a counting or sampling problem of bases of a matroid, where instead you assign a weight to your bases and more. And I apologize if this is probably incomplete in this. Okay. So what is our main result? Our main result is that, yes, indeed, that there is a polynomial time randomized approximation algorithm that gives you a 1 plus or minus epsilon multiplicative approximation. Okay. And let's just recall that sort of the applications of this are just like you want to recover from erasures in linear codes, or estimating graph reliability, or random forest measures. Okay, so I guess our first step towards like counting the number of bases is to reduce this to a sampling problem. Okay, so recall the problem is to estimate the number of bases. Let script B be sort of the collection of all bases of your matroid. Okay. Let M, so /E, denote the contraction of your matroid. So this is the matroid given by, you look at all independent sets of your original matroid. You only keep the independent sets which contain your element E, and then you remove E from them. This is a smaller matroid called the contraction. Okay. Now what you can do is you can write the number of bases of your original matroid as sort of this telescoping product. Okay. And what you observe is that sort of each term in this product is a marginal probability of some element being in a random base of some matroid. Okay. So sort of it suffices to estimate these marginal probabilities, and then you can just compute this product. Okay. And how to estimate these probabilities? You can just, this is sort of how you reduce to approximate sampling. If you can approximately sample, then you just sample a base, see if your element is in the base, and just keep sampling and to get better and better estimates of your marginal probability. So now we reduce it to a sampling problem. So our approach will be via Markov chains. Okay. And what you have to do for the Markov chain, you have to define sort of a graph on which you will do your random walk. Okay. And this random walk will be what we call the basis exchange graph. Okay. So what is this graph? You're given a matroid, and the vertices of this graph, the state space, corresponds to all bases of your matroid. And you have an edge between two bases if and only if they intersect in an independent set of size rank -1. Okay. So just to give you a concrete example, you have two graphs here. I draw two spanning trees. These two spanning trees are adjacent to each other in this graph, in this basis exchange graph, because you just exchange the blue edge for the green edge. This is like a local update, local move between bases. I guess a more concrete geometric example would be this graph. So this comes from, if you look at the partition matroid, okay, so I guess here's one way to say it. You have n bins. Each bin, you have, say, two options. You have like a blue ball or a red ball, and you're allowed to choose at most one ball from each of your n bins, okay, like blue or red. Okay, and now you can encode, and your bases are exactly when you choose exactly one ball from each bin. And so you can code this as a bit vector, and then two bases are adjacent if only if they just differ by like which ball you choose in one bin. So you can code these as bit vectors, and this gives the corresponding basis exchange graph is exactly the hypercube. Okay. Okay, so now I've sort of defined what graph we're going to do our random walk on. Let's write out the algorithm most explicitly, step by step. So you start at a base, okay? Any base that you want. You could be deterministic. Just pick a base. You throw out a uniformly random element, and then you transition. So you start at a base. You throw out a uniformly random element. So this gives you a size rank -1 independent set. And then out of all bases that contain you pick a uniformly random one and you transition to it. Okay. And then we will capture the transition probabilities of these steps via this matrix, PR of down up. So down up is to signify that we first throw out an element and you come back up, you complete to a base. Okay. So let's just maybe just to make it very explicit, or just do an example. So here I have the uniform matroid on rank 3 on 4 elements. Okay. And on the right here, I have the table. So you can think of a Markov chain as every time step you have a distribution over all possible bases that you could be at that time step. And then every time you take a step in the Markov chain, you're evolving this distribution over time. Okay? So let's just do an example. So here I start at 1, 2, 3, 4, or not 1, 2, 3, 4, 1, 2, 4. Okay? I look at all, I guess what I'll call these are near bases, so independent sets of size rank -1. I look at all near bases that are underneath. I pick a uniformly random one, I transition to it. I pick a base that contains me, I transition to it. And sort of, you see that sort of the distribution on possible bases you could be at a given time step is evolving. And this process continues. And note that you can return to the same base that you were at before. Okay. So, yeah, and you sort of notice that these probabilities are evening out. That's actually what we want it to do. Our goal is sort of, in the end, for this thing to converge, in some sense, to the uniform distribution over all bases. Okay. So I have to tell you what convergence means. So let's first define a metric on probability distributions. This is where, so a very common probability distribution is the total variation distance, which is sort of, you can think of as just the maximum discrepancy that two probability distributions can take on any given subset. Okay. And then we define the mixing time as just the minimum time it takes for your Markov chain distribution to, say, be epsilon close to uniform. Okay. And it's sort of a well-known fact that you can bound the mixing time, you can upper bound the mixing time by the inverse spectral gap of your transition probability matrix times a logarithmic factor like log of 1 over epsilon and log of the size of your state space. Okay? So in this case, this logarithmic factor is okay because the number of bases is at most n to the power r. So sort of the main thing we have to do is sort of upper bound this inverse spectral gap, or in other words, bound the second largest eigenvalue of the transition probability matrix away from 1. Okay. And this is exactly what we'll do. What we'll prove is that you can bound it away from 1 by 1 over r, at least. Okay. And this immediately implies sort of what we want to show, which is that there is this polynomial time randomized algorithm. And also it actually also implies that this basis exchange graph has this combinatorial property of having edge expansion at least 1. So our focus will be on this. Okay, so at this point, so let me sort of briefly recall some of what was talked about yesterday. So our approach is based off of what Professor Kaufman and Professor Oppenheim talked about yesterday. Okay, let me just sort of briefly go through it again at a high level. Okay, so what is the idea? The idea is to prove this bound inductively. Okay. So first you reduce it to dimension r minus 1. Okay, so how do you do this? So recall that the way that we laid out this algorithm is you start at a base, you throw out a random element, and you come back up. Okay. So you can think about this as sort of, first you have this Markov chain on the bipartite graph between near bases and bases, where you have a near base is connected to a base if only the near base is contained in the base. Okay. And then the walk that we're interested in is just given by you start at a base and you take 2 steps each time inside this bipartite walk. Okay, so this bipartite walk induces the random walk that we're interested in by taking 2 steps. Okay. But sort of what you can do is also you can say that, okay, I can also start at a near base, take 2 steps, go up and come back down. Okay. And so this induces a random walk on also near bases. And these 2 random walks are very much related. So if you look at their transition probability matrices, they're both self-adjoint with respect to some inner product. They both have positive or non-negative eigenvalues. And in particular, the most important thing for us is that they have the same non-zero eigenvalues with multiplicity. And so if we wanted to bound the second largest eigenvalue of the transition probability matrix that we're interested in, it suffices to bound the second largest eigenvalue of the random walk defined on near bases. So let's go down dimension once more. So originally we had this bipartite graph between near bases and bases. But we could have done the same construction between size rank -2 independent sets and size rank -1 independent sets. Okay. So we could have defined, for example, the down-up walk, and we said the up-down walk. Okay. So here, right. So we have this. So now in particular we have two random walks on near bases. Okay, on size rank -1 independent sets. One given by you first go up to a base and you come back down, and then the other given by you go down to a size rank -2 independent set and then come back up. Okay. And sort of to keep the induction going, what we have to do is sort of relate these two chains as well. Okay? They have the same state space, and in particular, they have the same stationary distribution. Okay? The sort of way you have to get that is sort of you have to weight your independent sets, and the weight you give them is proportional to the probability that you see this independent set when you sample a uniformly random base. Okay? So, or you think of it as proportional to the number of bases that contain you. So this sort of makes all the weights consistent. Okay? And this ensures that it induces the same stationary distribution in all independent sets. Okay, so sort of the main thing we have to do is prove a relation with them, between them. And this is the relation for matroid that we will prove. Okay. And again, I emphasize that we could have done this whole thing not just at the top level or dimension r-1 or dimension r-2, but at all levels of the matroid. So you have dimension k or rank k, where you define a bipartite walk between independent sets of size k, independent sets of size k-1, bipartite walk, take 2 steps to induce random walks on independent sets of size k and independent sets of size k-1, and so on. Okay? So the more general statement of the main thing we want to prove is given down there, where it holds for all dimensions.
These weights are induced by the walk, right? They're not something you impose from outside.
So I mean, so at the top level, right, we want uniform distribution of all bases. So they're induced by that distribution. Okay, so before I say more, let's just see how if you have that main lemma, then you can exactly get the bound you want just by unraveling the recursion. Just doing the induction and bounding from the bottom to the top. Okay. So our goal is to prove this relationship. Okay. And this is sort of where the machinery of the Kaufman-Oppenheim theory comes in. Okay. So yesterday they introduced high-dimensional expanders, but let me just sort of recall the setting there. Okay. So the setting is you have a simplicial complex. So what is a simplicial complex? A simplicial complex is, you can think of it as a generalization of a graph. Okay. Here you have a set system. You have, again, it's downwards closed, where if you have an element in your set system, a subset of that element, then that subset's also in your set system. So note that in particular, matroids are simplicial complexes. Okay. So matroids are simplicial complexes with an added property of exchange. Okay. So here I drew the simplicial complex again for the uniform matroid on 4 elements of rank 3. Okay. A couple operations that we will be needing, which we recall from yesterday, will be, one of them will be the link. So the link is, you just think of it as follows, or you pick some, say, reference element in your simplicial complex, and then what the link is a simplicial subcomplex given by you take all of the faces that contain your reference face, and then only those, and you remove your reference face from them. Okay, so sort of more explicitly. So note that in particular, for example, if you take the link of your complex with respect to the empty set, this gives you your complex back. Okay, and also for matroid theorists, another way to say the link is also the contraction. Okay? So just to make it very explicit, let's say we're taking the link with respect to the singleton 3. You take all of the faces above it that contain it. So this is level 1 above and a level 1 higher. These are the only faces that you keep, so you throw out everything else. And now every face contains 3, so let's just remove 3 from it. This is redundant. So the next operation that we'll be needing is also the 1 skeleton. And this is simply just, you have a simplicial complex. You only look at the size 1 and size 2 elements of your simplicial complex, and this gives you a graph. So for example, here we just have the vertices and the edges. We throw out everything else, and then these edges are what connect your vertices. Okay, so now having sort of set up the definitions that we'll need, now let's talk about high-dimensional expanders. So what is that we want to do? We know that in sort of the world of graphs, we know that if you have expansion, then this immediately gives you rapid mixing of the random walk on your graph. And sort of what you want to do is the same thing here. So if you have a high-dimensional expander, then you want to say that the global random walk is also rapidly mixing. So let me say that, for example, the global walks that I described earlier on matroids can be said in full generality for any simplicial complex. Okay? And this is exactly what the Kaufman-Oppenheim theory gives us. Okay? So let's make precise what we mean by high-dimensional expansion. Okay? So we use a local criterion, which is sort of in some sense easier to verify. So what do we want? We want that for every link, which you think of maybe as localizing your complex, if you look at the graph that you get from that link, this graph is a good expander in the usual graph sense. Okay. So let me sort of say some of the, maybe some intuition that Professor Kaufman mentioned yesterday. So why this definition? So maybe here's some intuition, which is, suppose, let's say you're looking at the global random walk or the global graph of all size k elements of your simplicial complex, okay? And you want to say that this thing is this graph is a good expander, okay? So let's just take 2 elements, tau and sigma, okay? And let's say there is some edge. So we assume the simplicial complex is connected, but sort of what we want in the end is that it's very well connected. So let's say that there's some edge in there, okay? So if you look at their intersection, this gives you an element of 1 dimension less. And what you're sort of saying that, so let's say that their intersection is contained in some other elements. So what you're saying is that so this is the link. If this link is a good expander graph, then what it should, in some sense, enforce is that there should be some other edges that also cross this cut. So the local expansion you should have at least some edges across the cut, okay? Like more than just one. Okay. Okay. So what they proved is that we have this relationship between sort of the global random walk on level k going up down, and the global random walk on level k going down up. Okay. And so recall that what we actually wanted is the following. So it suffices to take, so what we want is to say that we have lambda equals 0 for our problem. So our goal is to show that matroids are 0 local spectral expanders, in other words. Okay. So sort of to prove this, what we'll do is we'll now introduce polynomials into the picture, and we'll see how properties of polynomials translate to properties or local properties of our simplicial complex. Okay. So let's sort of fill out this mapping. So let's first see how if you get a simplicial complex, you can go to a polynomial. Okay. Okay, so if you have a simplicial complex, I'll define a sort of a generating polynomial for its maximal faces by just get a variable for each element of your ground set, and then you sum over all maximal faces of your simplicial complex, and you take the product of the variables of the corresponding to elements in those faces. Okay. So let's do an example here. So here, we have a graph. Let's look at the graphic matroid of it. So the elements of our ground set are the edges of this graph. Let's give them some labels. So 1, 2, 3, 4. So now we'll have variables z1, z2, z3, z4. And for this graph, we have the bases of this matroid are just the spanning trees of the graph. So we have 3 spanning trees here. Each spanning tree gives us a monomial in our polynomial. And so now we just add it up. And that's exactly our generated polynomial. And you can also go the other way. So if you have a polynomial, you can build the simplicial complex in the same way. So if you have a polynomial, you take each variable corresponds to an element of your ground set. Each monomial corresponds to a maximal face of your simplicial complex. So for example, here we have just this polynomial. You get an element or a vertex of your simplicial complex for each variable. You get a maximal face for each monomial, and then you just take downwards closure and you get everything in between. So sort of now we have this correspondence between simplicial complexes and polynomials. Let's build up sort of a dictionary of mapping concepts from simplicial complexes to concepts from polynomials. Okay. So for example, I guess something not too difficult to see, just the dimension of the complex is just equal to the degree of your polynomial. The purity of your complex corresponds to homogeneity of your polynomial. Somewhat more interestingly is that if you, say, look at the number of maximal faces, this corresponds to evaluating your polynomial at all ones. Okay? So in particular, you can cast the goal of counting to, and more generally, as a problem of evaluating your polynomial. Okay? Just to make sure that this is clear. So again, we have the same graphic matroid. We have 3 spanning trees here. This is the polynomial. If you evaluate all at once, you get exactly 3. Okay? Just because you have 3 monomials. Okay. Another nice sort of correspondence is that the operation of sort of localizing your complex by taking link corresponds to differentiating your polynomial. Okay. So let's see that in action here again. So we have the graphic matroid for this graph. We have these 3 spanning trees, and we have the corresponding generating polynomial. Okay. So let's sort of take the link with respect to 1, the edge 1. So since every spanning tree contains 1, you just get a monomial for everything stays, and you just take out the edge. I guess another example is like if you want to say differentiate with respect to say z2, then you just contract this edge because you always want that in your spanning tree. And then since this one does not contain 2, then that's not allowed, and then we're only left with monomials corresponding to the spanning trees of the contracted graph. And sort of putting these 2 together, you can see that also that, so here, the numerator is just, if you take the partial derivative with respect to, say, some element, and you evaluate all once, this gives you all bases that contain your element. And in the denominator, you just get all bases. So in particular, this is the marginal probability of seeing your element in a uniformly random base. Okay. And so the final, most interesting thing is that the weighted adjacency matrix of your skeleton corresponds to the Hessian, okay, of your polynomial. So because here, you have this polynomial, you just compute the Hessian, and this sort of follows from previous items in our dictionary. So So I guess you could sort of think that maybe on the left-hand side you have a sort of more combinatorial perspective, and on the right-hand side you have sort of a more analytic perspective. Okay, so let's add one more entry into this dictionary. Okay, so let's recall from yesterday sort of log-concave polynomials or Lorentzian polynomials or are sort of give a lot of nice. They were used to, for example, prove a lot of nice combinatorial inequalities, and we'll see that they are also very useful here. So let's just recall that a polynomial is log-concave if the Hessian of the logarithm is negative semi-definite. Okay? Or equivalently, the Hessian itself is bounded by this rank 1 positive semi-definite matrix. Okay? And what is strong log-concavity? This is, you say a polynomial is strongly log-concave if also every derivative is log-concave. And we saw yesterday, I think, from Junha's talk that this is equivalent to say the polynomial is Lorentzian or the polynomial is completely log-concave. Okay? And so the nice thing is that if you have log-concavity, then you know that the Hessian has at most one positive eigenvalue, just by virtue of the fact that it's bounded above by a rank 1 positive semi-definite matrix. Okay. So now you can kind of see that if you have strong log-concavity, then what you're saying is that also that every link, or every derivative, the Hessian has at most one positive eigenvalue. So you can also recall from, I think, Cynthia's talk, or I think also Junha's talk, we know that the basis generating polynomial of any matroid is strong log-concave or completely log-concave or Lorentzian. Okay. So in particular, yeah, as I said earlier, the Hessian of every derivative has at most one positive eigenvalue. So in particular, if you use our dictionary that we saw earlier, I'll remind you on sort of the next slide. We know that the second largest eigenvalue of every localized random walk matrix is bounded by 0. Okay. So in particular, this gives us exactly what we want. Matroids are 0 local spectral expanders. Okay. Any questions so far? So let's just go back to our dictionary. Now we can sort of add another entry to our dictionary. You say that 0 local spectral expansion is strong log-concavity. Okay. So just a quick recap. So after all this, you sort of see that we have a polynomial time randomized algorithm to produce a good approximation of the number of bases of any matroid using Markov chain. This actually also works in the weighted case. So you can actually also weight your bases. And then what you would do to weight all of independent sets lower is just to add up the weights of all the bases that contain you. Okay. So I guess the more general theorem is that if you're given oracle access to the coefficients of, let's say, a strongly log-concave polynomial, okay, so you're allowed to ask for the coefficient of a given monomial. Then you can evaluate this polynomial actually at any point in the positive orthant and give a 1 plus or minus epsilon approximation to it. So I guess, so there are many other applications beyond sort of what I said at the beginning of the talk. So for example, now you can count forest, compute a reliability polynomial. It turns out that also the Q-Potts model partition function for Q between 0 and 1 is strong log-concave. This is also proved by Junha and Peter Brandin. This actually also implies a strong log-concavity of the Tut polynomial in a certain regime. And also we can get that if you have a determinantal point process, that you can also smooth the weights by raising the coefficients to some power between 0 and 1. So I guess there's sort of many open problems left still. So for example, we actually also know that I think, so this was mentioned I think in Nima's talk at the boot camp, that if you have a strongly log-concave polynomial, I think it's also mentioned in Junha's talk as well. If you have a strongly log-concave polynomial and you look at the support, you look at all monomials with non-zero coefficient, these the support has to form the basis of some matroid. So in particular, what this says is sort of that all the mixing time bounds that we have sort of only work for the case when your support form the basis of a matroid. So but there are many other combinatorial structures beyond matroids that many other combinatorial structures beyond matroids. So in particular, for example, could you use some of this machinery developed by Kaufman Oppenheim and also theory of polynomials to say something about counting non-broken bases, okay, or counting proper colorings of a graph, or anything. Another question is that, so far what I've showed you in the talk is that we bound the second largest eigenvalue, but actually all of our inequalities, all the inequalities allow you to bound every eigenvalue of your tangential probability matrix. Okay. But so far we haven't used any of that information. So I guess another question would be, could you improve the mixing time if you leverage information about all the other eigenvalues and even eigenvectors, for example? So I guess another question is, can you get mixing using approximate negative correlation? Okay, so what does that mean? So I guess maybe this is where I can just sort of write something on the board. So negative correlation is essentially the following inequality, which says that if you look at the probability of seeing, say, an element in your base, in your uniform random base, conditioned on, say, some other element being in your base, this is less than or equal to just if you had not seen f at all. Okay, this is called negative correlation. Okay. And sort of the seminal work of Feder and Mihail says that if holds for all minors, if you have negative correlation on every contraction and every possible sequence of contractions and deletions of your matroid, then you have mixing for your Markov chain. And the proof is also inductive on, has a very similar induction. But sort of the problem is that it's known not all correlation. Yeah. But sort of an interesting thing is that they satisfy something like an approximate kind of negative correlation, which was observed independently by Junha and Peter Brandon, and also by Cheyenne, Cynthia and Nima, which is that So it's approximate in the sense that you get an extra factor of 2 here. Okay. I guess, so what I'm asking here is if you can say, maybe use this approximate form of negative correlation but coupled with the same technique from Fedor-Mihail to get the same mixing result. Maybe I should say also that this.
How tight is that 2?
I'm sorry?
How tight is the 2?
How tight is the 2?
So I have conjectured that it's 8/7.
Yeah.
There is an example achieving 8/7. There's a sequence of inputs whose limit is 8/7.
And you think 8/7 is the right answer?
My guess is that's optimal,
Independent of the rank.
independent of the rank or anything.
I guess the last thing I want to mention is that sort of the full Mihaly-Vazaryan conjecture, which just says that you have any 0, 1 polytope. So the vertices of your polytope have coordinates with only 0s or 1s. Then if you look at the skeleton, the graph obtained by just connecting your vertices, that has also edge expansion at least 1. So what we proved earlier, which was that for matroid polytopes, we have edge expansion at least 1. But so the full conjecture for 0, 1 polytopes is still open. This. I guess I had 15 minutes of questions because I ended much earlier than I expected. So.
You know, there's some cases where the mixing time bounds you get are tight.
Oh, sorry. Say it again.
There's like some cases where the mixing time bounds you get are tight.
Are tight. So we think that we can improve it. So sort of, I guess, write more explicitly what the mixing time bound get is. So we get actually there's no constant in front, so it's and we're sort of trying to see if maybe you can get rid of the square. Because we sort of know so much more information than just second largest eigenvalue. Right? So.
Right.
So you can actually bound all eigenvalues so that so you can bound average mixing time. But that's a useless information. If you could run from a random starting point.
That would help.
Right, there is a question of bounding the not the Polynomial constant, the other one, the Log-Concave constant, yes. So the thing is, hypercube is tight. So like any proof you give here, like extend hypercube.
Hypercube is tight for this.
Yeah. Oh no, not the mixing. The eigenvalues are tight.
Oh, right.
So you have to.
Oh, I see.
The thing is,
it's at least as good as improving on L2 mixing.
yeah,
time.
yeah. The thing is, for hypercube, like it's tricky to get down to. Like either you have to use vertex transitivity or you have to use lots of.
I have a question. So, what type of actually? So you get for your matroids, you get expand your higher dimension expanding to fourth quality. I mean, what are their parameters?
Oh, sorry. Actually, yeah, I should probably mention. So. Yes, get zero local spectral expansion. But so I guess I should comment that at least to my knowledge, the people in the high dimensional expander community, they want, I guess, like bounded degree expanders. Is that right? And these are binomial.
So I mean, so can you say like, but roughly, I mean, if the number of vertices is n, what would be the degree? Or
The number of vertices is n will be the degree.
Okay, if you didn't. Okay, but you should get a collection of new high-dimensional expanders which are not bounded degree, but yet we don't know many of such things either. So.
Right.
The degree is at most r times n. R is the rank, n is the number of elements.
I think when you say degree, do you mean just like number of like maximal faces that contain, say, any elements? Or
Like the one skeleton graph of your complex.
Oh, one skeleton graph of each link.
The one skeleton, so you get a complex for
Yeah.
all unit, and like so if you look on the one skeleton of that complex, what
Of the top faces. Yeah, that has to be r times
No,
n.
okay.
Okay. So we know that, for example, if you take the skeleton of any matroid, that it's actually a complete multi-partite graph. So it's very, very dense. If that's what you're asking.
Yes, but you don't get, so your complex is not the complete complex.
Right.
So what is, like every vertex in your complex, in how many top dimensional cells it is participating. So I mean, if we have n vertices, how?
Right. Okay, so let's say you have n vertices and rank r, okay, or dimension r. So I think from previous works of Cheyenne, Nima, and Cynthia, they have this entropy inequality, which actually allows you to bound, like lower bound the number of bases of any matroid by some, I think, exponential, like base, so exponential in r.
It depends on the marginal. If your matroid can have just one base, but if it is like that marginals of elements are, like, say, at most 1/2, for example, then you're going to have exponential. Yeah, this basically says you cannot get like a sparse expanders if you want 0. So like for your applications, you actually have to go above 0 if you want to get a sparse.
And is there any way that your things would be relevant for non-zero local spectral expander?
I'm not sure. We don't know what the, I guess, the analog of this Log-Concavity for you allow larger than 0. We're still thinking about that.
Well, yes, one thing is you have a different language, so you may be able to prove things here that, I don't know. Other questions? Right.
So in fact, that was already known.
Well, I mean, you know, that the generalization it also like simplifying the figure.
But you don't think
I still have that problem. I'm trying to
it's not easy.
But you know, it's like, it's kind of like an induction. I
mean, but the ground elements.
There is a new paper that is log similar.
Oh, this is support. I see.
I mean, actually,
Okay.
like,
It works for all
okay, so actually,
for graphs.
so, yeah, I think our result is something that's not a matroid, but maybe it's a color.
Yeah.
This thing of just the uniform R matroid, which is basically what we're generalizing. I guess it would be color.
It was posted last Friday. Like Jonathan Herman.
Okay, sure.
Yeah, but still. So we had log, it actually it was modified log level, not log level. Oh. So there is an issue that the log level of itself is not good for your application. So in these polynomials, your coefficients can, like the probabilities can be very small, and it's lower bounded by that. So that's why you don't want log level. They are modified.
Well, so I guess
That's fine.
that seems
I mean, you can write it.
Oh yeah, of course.
But that's not exactly why.
Yeah, sure. Yeah.
It doesn't give L2 minutes.
That's very strange.
Yeah, that is very strange. Is that you proved that in your Probabilistic paper?
And it still gives you log level.
Is that
Actually, the other nice thing is it also gives you concentration lines. So when you have that.
Concavity intensity or is like
I'm not sure.
did you think about it?
Yeah, so we had a tool for Inductive matrix that rounds
It seemed like because
eigenvalues.
Oh, okay. Okay, great. The one that came out.
Yeah, there was. The problem is I wanted to do
Yeah, so there is like some contradiction. Yeah, that's in the end of the long argument.
yes, it implies that, but you can just do yeah, so you can just do on basis exchange graph.
Yeah, I'll have to think about it.
Uniform
Anyway,
weighting, we
thanks
have
a lot.
a different weighting, but it's that, I mean, okay, you also get that. So, I mean, if you do uniform weighting for basis exchange graph, it makes it slower, but it's really good. Actually, something I wanted to ask you, how do we prove that the vertex expansion of the hypercube?
Oh, it's real easy.
There are many near.
Oh, wait, hold on, no. It's not easy. Yeah, it's annoying. No, it's pure combinatorics. Like shifting might be like. It's pure combinatorics. Yeah, like you show that you take a set and you do a shifting operation, it improves the vertex expansion, you can keep doing that and turn it into a ball or whatever. Yeah, it's a drag.